What's up guys, it's me Sir Ernest, and today we're going to continue solving problem 3.8 of Griffiths 4th edition. So in this case, we want to find the induced surface charge on the sphere as a function of theta. Then we're going to integrate this to get the total induced charge. And we will know what it will be. Okay, so just a quick review. So this is our configuration wherein we have a charge Q here, and we were asked in letter A how to what is now the potential anywhere, okay, given that this sphere is grounded. So we say grounded, the potential on this sphere with radius r is 0. So the potential at r is equal to 0. Okay, now because this is a conductor, this charge Q will actually induce charge on the sphere, and that is what we're going to look for. What will be the induced surface charge on this sphere? Okay, so by equation 2.49, the surface charge density at a surface is equal to negative epsilon naught times the partial derivative of v with respect to your normal coordinate or normal direction on the surface. So if this is a sphere, the normal direction is actually the radial direction, okay, relative to the center of your sphere. Okay, so that means the surface charge density sigma will now be equal to negative epsilon naught times derivative of v with respect to r. And because we're looking for the surface charge on the sphere, so that means we have to evaluate this when r is equal to capital R. Okay, so now let's substitute this from our previous video. We know that v will be a function of r and theta. So when we substitute that here, the surface charge density sigma will now be equal to negative epsilon naught times the partial derivative with respect to r of 1 over 4 pi epsilon naught times q over square root of r squared plus a squared minus 2ra cosine theta minus q divided by square root of capital R squared minus r a over r squared minus 2 ra cosine theta. Okay, and then we're going to evaluate this when r is equal to r. Okay, so by doing that, I'm going to skip a step here, and then this will just be equal to q over 4 pi because epsilon here will cancel, and then negative signs that will be brought about by these two terms. The sigma will now be equal to q over 4 pi times r squared plus a squared minus 2 a r cosine theta to the negative 3 halves times r minus a cosine theta minus a squared over r plus a cosine theta. And you will notice here that this will just cancel. And therefore, we can now simplify this term or this expression as q over 4 pi capital R times r minus a squared divided by r squared plus a squared minus 2ar cosine theta to the 3 halves. And this is now the induced charge density. Okay, so this is the induced charge density on the surface of this sphere. Okay, very simple, right? Very direct calculations. Now, what happens now if we're going to integrate this to get the induced charge? So this induced charge q prime is just the integral of the surface charge density dA. So this is a surface integral. Okay, so this is now equal to integral of this. So this is q over 4 pi capital R times r squared minus a squared times r squared plus a squared minus 2ar cosine theta to the 3 halves times the surface area element. So that's capital R squared sine theta d theta d phi. So this is a double integral because this is a surface integral. Okay, and this whole thing are only functions of theta except for this d theta. So that means when you integrate d theta for this whole sphere, that is just equal to 2 pi. And that will be cancelled with 4 pi here with 2 remaining here. Okay, q r squared minus a squared are constant, so we can take that away. Okay, so they're the only thing, and also r squared here, which will also cancel. Which will also cancel with r here. So the end result here will be this will be equal to q times a squared minus r squared divided by 2a. Again, you can do the integration later. Okay, so now this is now times r squared plus a squared plus 2ar 1/2 minus r squared plus a squared minus 2ar to the 1/2. So how did we arrive at this? So remember that these two angular directions or variables have limits of integration. This one will be from 0 to 2 pi, and this one will be 0 to pi. So when we integrate this with respect to theta or relative to theta, the integration will happen from 0 to pi, whereas for theta, for phi, that will be integration from 0 to 2 pi. That's why we integrate d phi. This will just be equal to 2 pi. Okay, and since, as you will notice here, that a is greater than r, so that means this square roots, this is a perfect square. Remember, this is a perfect square. That's r plus a squared. When you take the square root, it can be plus, it can be minus. but we already set that A is greater than R. So this charge will just be equal to Q times A squared minus R squared divided by 2A times, sorry, this should be to the, this should be negative 1/2. This should be negative 1/2. So this is 1 over R plus A minus 1 over A minus R, which is equal to, if we're going to this is Q times A squared minus R squared divided by 2A, which is equal times, sorry, it should be times 1, and so this is A minus R minus R minus A divided by A squared minus R squared, sum and minus, right? So this and this will cancel, this becomes, so this and this will cancel, so this becomes negative Q R squared, negative, sorry, then not R squared, this should be R, 2R, this negative 2R, and then there's a 2 here, so that 2 will cancel, so this is equal to negative QR over A, which is what we set in example 32. This is equal to Q prime. Okay, so naturally the induced charge here will be equal to negative of this charge, right? Amazing, right? Everything is consistent. That's it. That's problem 3.8 letter B of Griffiths 4th edition. And in the next problem, in the next video, we're going to solve the last part of this problem, wherein we're going to calculate the energy of this configuration. But for now, thank you for watching. I hope you learned something today, and I'll see you guys in the next video. Bye-bye.